The choice of generalized coordinates is subject to no restriction. They may be any quantities that fix the position of the system. Passing to any other independent set leaves the form of Lagrange's equations unchanged, and such a change is called a point transformation. Since Lagrange's equations are unchanged, Hamilton's equations are unchanged too. But the Hamiltonian treatment, in fact, allows a much wider range of transformations, because there the momenta are variables independent of and on an equal footing with the coordinates. So we may transform all 2s of the variables together. The new coordinates and the new momenta may each depend on the old coordinates and the old momenta. This enlargement is one of the important advantages of the Hamiltonian treatment. Not every such transformation keeps the equations in canonical form. However, let us find the condition. What is needed for the new variables to satisfy Hamilton's equations as well? At the end of the last lesson, we saw that Hamilton's equations follow from the principle of least action, with coordinates and momenta varied independently. If the new variables also obey them, the same principle must hold in the new variables. The two forms are equivalent if their integrands differ by the total differential of some function. The difference is then a constant fixed at the endpoints, which cannot affect the variation. Such a transformation is called canonical, and that function is its generating function. Rearranging that relation lets the coefficients be read off directly. The old momentum is the derivative of the generating function by the old coordinate. The new momentum is minus its derivative by the new coordinate, and the two Hamiltonians differ by its time derivative. Sometimes the old coordinates and the new momenta are the more convenient variables. One Legendre transformation gives a second generating function, whose derivative by the old coordinate is the old momentum and whose derivative by the new momentum is the new coordinate. Whichever form is used, the difference of the two Hamiltonians is always the partial derivative of the generating function with respect to time. So if it does not contain the time, the new Hamiltonian is the old one with the new variable substituted in. The range is so wide that the distinction between coordinates and momenta is little more than a name. One such transformation simply interchanges them. Hence, they are called canonically conjugate quantities, and the canonical condition is written cleanly with Poisson brackets.